Hello and welcome to Lecture 24. In this lecture, we're going to cover sections 27.1 to 27.8 with a focus on the problem-solving techniques used in solving numerical examples that cover the content of quantum physics and using the formulas that are listed below. This lecture will be divided into videos where each video focuses on one topic of the chapter. Furthermore, if you would like to learn more about the topics and background of the ideas that are going to be involved in the examples in these lecture videos, please look at the two lecture videos that accompany Lecture 23, which is a series of slides. Okay? All right, so in this first video, we're going to talk about Wiens Law. Okay? So, Wiens Law is going to be the topic. Wiens Law, we're going to use it to relate the peak wavelength emitted by a black body to the temperature of that black body. Okay? Now remember, a black body is an idealized concept of a perfect emitter. This is going to be the formula that we're using. Let me make sure and label the important variables in the formula. Okay? So here we have Wiens Law. Let's just give an arrow to it. Wiens Law. Okay. Lambda sub m is the peak wavelength. Okay. And if we look here, we're seeing that the peak wavelength times temperature, and that would be temperature measured in Kelvin. Okay. Peak wavelength is going to be in meters. Okay. Point that out so you don't assume it's going to be in nanometers. Is going to be always equal to this value. Essentially, it's always equal to a constant. I do have a small typo here because these are not meant to be variables, so I'm going to clarify that a little bit, and then I want to fix one other thing as well. I caught a lot of typos, but this one slipped through, and I wanted to go ahead and start recording. Okay, and this shouldn't be the variable T, but should actually be the unit of temperature, which is the Kelvin. So it should be like this. So it should be meters Kelvin. There we go. So again, this is just a constant, and that constant happens to have units of meters Kelvin. So again, peak wavelength times temperature is always equal to 2.9 times 10 to the negative 3 meter Kelvin. Okay. So pretty straightforward relationship, remarkably useful, and let's put it to use. Okay. So I have two examples that I want to show you that regard Wiens Law. So we'll flip to our page with our first examples. So the one that we're going to do is example 1 and 3, and I'm leaving example 2 for practice that you can do on your own. Okay, so let's take a look at example 1. So in example 1, we're told that a human body with a surface temperature of 309.8 Kelvin can be treated as a black body. What is the peak wavelength emitted by a human? Of course, there is no part B, so that shouldn't say part A. Okay, so we just want to find the peak wavelength. It's as simple as that. Okay. So if you do want to find the peak wavelength, you would just use lambda m, okay? And that's just going to be equal to our constant. So our 2.9, let's see, what was the value? Make sure I have, yeah, so 2.9, excuse me. So center, 2.9 times 10 to the negative 3 meters Kelvin divided by the temperature in Kelvin. I guess I could have given it to you in Fahrenheit and asked for a conversion, but I went ahead and gave it to you in Kelvin. I believe this is typical, like non-high body temperature. Yeah, because 273, and then we add 36 degrees, which is body temperature in Celsius. Yep, that should get us right around 310, right? So human healthy body temperature, no fever or anything. Okay, so when we go ahead and put in those numbers, we get 9.36 times 10 to the negative 6 meters. Okay? So you can see how those units are going to work out. All right? Okay? Again, no conversions necessary. So that's our answer. We can go ahead and put a box around it. It's very much a plug and chug answer, or plug and chug problem. We can convert that to nanometers to kind of compare it to visible light. It ends up being 9,360 nanometers. Now it's very good, in fact, especially as we're moving in, talking more about light, whether it's the light involved in Compton scattering or the light involved between energy levels of atoms in the next chapter. It really, really will benefit you if you have an idea of where different types of light fall on the spectrum, especially in terms of wavelength, because that's going to be the most common time we refer to light. We could be talking about light in terms of its frequency, because of course the speed of light equals wavelength times frequency. So if you know wavelength, you know frequency automatically. But my point is that the wavelength is the go-to way of categorizing light. It's kind of it's the shorthand, it's the parlance, it's the way we talk about light. So when I look at this and I see that it's thousands of nanometers, I immediately recognize that that's infrared. Now, I don't know light so well as to say if that is near infrared or far infrared, but I know it is at least infrared, okay? So looking at this light right away, we can identify it as infrared. So that is light that is invisible to the human eye. It's a lower energy light than visible light, than the rainbow that we can see. Certainly some organisms can see infrared light, and you can design certain devices to pick up infrared light. Certainly you can have a computer sensor that can pick that up, okay? But that's it. That's the idea. We are constantly emitting light, right? So we are constantly emitting energy at this particular wavelength. Okay. All right, so plug and chug one. Example 2 is similar, but a little extra step there. I talk about how cold it has to be in order to get a particular wavelength. So you're solving for the temperature instead of solving for the wavelength. But now let's look at example 3, which has a little bit of extra information, things that we've seen way back earlier in a previous semester. Okay, so a 120 watt incandescent light bulb has a cylindrical tungsten filament 24.5 centimeters long and 0.33 millimeters in diameter with an emissivity of 0.26. Okay, and then the question is, what is the peak wavelength of this filament? Okay, so this has become somewhat of an archaic question in the last 10 years because we don't use a lot of tungsten filament light bulbs, but of course they were everywhere, as recently as your childhoods, and as recently as 10 years ago, right? Now, as far as talking about modernizing this to a fluorescent, it's quite a different system. It's a little bit more complex. So we're going to kind of keep this idea of things glowing. But the idea here, what's interesting about this question is you're going to see how ridiculously inefficient a tungsten light bulb. So you can at least appreciate, not that we're getting into the numbers of inefficiency, but you should at least appreciate why we've moved away from that as a technology, especially now to using LEDs. Okay? All right, so the formula that you have not seen for quite a while, and I would certainly forgive you for forgetting, is the formula of power flow, so energy per time, for radiative heat. So if you remember when we talked about heat flow, we had 2 ways of quantifying heat flow, and that was the conductive power formula and the radiative power formula. There was no such formula for convective heat flow. But here is the formula. So it's Q over T, so energy per time, or heat per time, because remember we use Q for heat, okay? And then that is equal to the emissivity times the Stefan-Boltzmann constant times the cross-sectional area of the surface area. It's actually not the cross-sectional area. That'd be more relevant to conductive heat flow. So the surface area of the object that's radiating, and then the temperature to the 4th power. If you're particularly good at remembering this stuff, you might remember that sometimes there was 2 temperatures. That was only when there was a surrounding temperature that was noticeable, such as surrounded by water. In the case of a light bulb, the chamber of the light bulb is nearly a vacuum, so we can treat the external temperature as approximately 0. Okay, so we'll go ahead and work this out. So we know our Q over T is specified to us as, because that's power, and we're told it's 120 watts. That's the correct units for the formula, because those are the base units of power. All right, so then it's just a matter of solving for the temperature. So this would look like we want to solve for T. So then I'd have T is going to be to the, so it's going to be the fourth root, or I'll just raise it to the 1/4 power. So it will be Q over T divided by emissivity, constant, surface area. Okay, so let's clean that up a tad. There we go. Okay, so now it's, oh, and of course to the 1/4 power, because temperature is raised to the 4th power. Okay, that's just laws of exponents there. All right, so let's put in our numbers. So we're told it was 120 watts. We were told that the emissivity is 0.26, okay, which is not great because it's kind of shiny, right? It would be better if it was a larger number, okay? And then our Stefan Boltzmann is 5.67 times 10 to the negative 8 watts per square meter Kelvin to the 4th, okay? And then we want our total surface area, and our surface area here is going to be the surface area of a cylinder without the caps. So it's going to be pi times diameter times length. And instead of it being 2 pi r, I'm just going to use diameter because we're given a diameter. So, so I'll go ahead and put that value in. So it would be pi times the diameter. So 3.3 times 10 to the negative 4, just convert it over to meters, okay? And then times the length of 25 centimeters, or 24.5 centimeters. Okay, so 0.245 meters. Okay, I'm going to go ahead and bring this down because I ran out of space. Okay, let's bring this down here. Okay, so that's everything we need. Of course, we're going to raise that to the 1/4 power. Let's do that, at least to show that we're going to do it. Okay, so it's all raised to the 1/4 power. Okay, so there we go. I've already calculated the number, and it turns out to be approximately to 2 sig figs, so their emissivity sets that, 2,400 Kelvin. So 2,400 Kelvin. Hot, right? Well, of course it has to be hot to be glowing, right? But what's the peak wavelength? Okay, so then our peak wavelength, now this part we'll just do what we did in the previous example. So we'll just take our 2.9 times 10 to the negative 3 meters Kelvin and divide by the temperature that we got, the 2,400. Okay. Okay. And that ends up being 1.23 times 10 to the negative 7 meters. Okay, that's our answer. And let's convert this over again to nanometers for discussion purposes. So it's 1230, okay? So, well, is that still infrared? Yeah. It is definitely closer to the visible spectrum because the visible spectrum is going to be ending somewhere in the 700s of nanometers. So it's not way off like, body temperature. That would be, a much lower energy type of infrared, but this type of infrared is still invisible. Well, that's not great, right? I mean, that means that the light bulb is predominantly producing light that we can't even see, where its purpose is to illuminate a room. Its purpose isn't to heat up the room. I mean, a heat lamp might, but light bulbs were never predominantly used for that. They're not put in efficient places for that. They're not part of a heating system. That's essentially wasted energy. Now, just because the peak wavelength is invisible infrared light doesn't mean that we couldn't see it, because there's essentially a bell curve of energy that falls on either side of the peak wavelength. Okay, refer to the slides in the previous lecture. And so they're well within that intensity bell curve was the visible end, which is why it would appear to be glowing red, faintly red. Okay? If you wanted it to be glowing any other color, you would have to actually move the peak within the visible wavelength. So really, most of the time you see something glowing red, that's actually going to be an object that has a peak wavelength that is in the infrared, but close enough to the visible spectrum that the tail of that intensity distribution is still picking up some visible light. Okay? So, yeah, so kind of interesting thing there. Definitely tungsten light bulbs not a great way to produce visible light. Maybe a better way to produce heat for that matter, right? But good thing we've moved on technology-wise. Okay, so that is the last example I'm going to do regarding Wiens Law. Please tune in for the second video where I'm going to discuss the photoelectric effect.